go for it. So we spent a bunch of time talking about chemical reactions, and then we were talking about solutions. Most of our focus of chemical reactions has been around what's called stoichiometry, the math of these chemical reactions. Today we're going to take a little bit of a math break here, and we're going to learn more about these chemical reactions. Specifically, one of the categories that we've already introduced, these double displacement reactions. Okay? Our goal is going to be to predict the products of these double displacement reactions. Is it unlocked? Cool. All right. So remember, these double displacement reactions are characterized by this pattern here. We have these two ionic compounds, AB and CD. And if we keep track of what happens to A and C here, we can see that in this reaction, they are going to swap places. So originally I have my blue A paired with the red B. Now I'm going to have that orange C paired with my red B. And A is now paired with D. All right, so in this reaction, we swapped our cations. A and C traded positions here. All right, that's going to be fundamental to how we draw our products for these chemical reactions. All right, and we sort of talked about this a little bit last time, but let's more formally introduce it now. The class of reactions that we're going to study more in depthly here are what are called precipitation reactions. Okay. And give me a second, this is going to drive me nuts. Reset this. Okay. These precipitation reactions, these are when we mix two aqueous solutions and we produce a solid product. All right, we took a look at these reactions before, but I gave you that full chemical equation and all you had to do was balance it. Now we're going to work on predicting the products of these precipitation reactions. All right, so predicting our products. Okay. I'm going to leave some space to make some rules here for predicting our products, but this is going to be our sample reaction. I'm giving you these two reactants. We're going to mix a solution of lead nitrate with a solution of sodium iodide. All right, if you did not already get one of these periodic tables, please grab one. These are our same periodic tables, but importantly on the back is this solubility table that you're going to need for today's class. Well, thank you. Pass these two down. Okay, so now we need to use this double displacement pattern to predict our products. What we're going to do is we're going to swap our cations. So I'm going to need to switch my lead and my sodium here. All right, but remember, we're going to put the formulas together for our products. What do we look at when we put our formulas together? It's all about the charges. All right, so step one in predicting these products, we need to break up these compounds into their cations and anions with their charges. All right, it's all about the charges. So I need to look at my chemical formulas here. Much like the same process we did when we were doing our nomenclature. We got to write down our ions here. We have a lead ion, and a nitrate ion, and a sodium ion, and an iodide ion. But the key here is going to be the charges of those ions. So everybody take a second, see if you can't fill in what are the charges of these ions here.
put the states of matter into for each?
We'll get there. We'll have to do the states of matter after we get our formulas together. But yes, we're definitely going to get there.
But not for the individual atoms.
No. We just need their charges so we can see how to put the formulas together. Okay, so sodium and iodide are kind of the easy ones because I can just tell based on the periodic table. Nitrate is a polyatomic ion. What's the charge of that nitrate ion? -1, cool. And that was one that we just had to know. But now, how could we figure out the charge of a nitrate ion? We got ourselves our solubility table, right? And again, if we look careful at our solubility table, it gives us the name and the formula for these ions here. So we got no more excuse for not remembering our polyatomic ions. Okay, so then the lead, much like our transition metals when we're naming, is kind of the pain in the butt part. We got to figure out the charge on this lead ion. And we don't know what it is based on the periodic table, so we got to look at the fact that we have these two nitrates, NO3, NO3, and each one has a -1 charge. So the total amount of negative charge in that compound's -2. So then how much positive charge must I have? +2. And since I only have one lead ion, the charge on that lead must be +2. Okay, cool. So we have these ions here with their charges. Okay, so we broke up our compounds into cations and anions with their charges. And now we're going to swap those cations. All right, so what do I mean by that? I'm going to put my sodium with which ion up here? The nitrate. And the lead is going to go with which ion? The iodide. Let me make some room. I can tell I'm about to run out. All right, so I'm going to pick up and swap my sodium and my lead. And now I need to put together my new formula for my products here. And since I wrote out these ions with their charges, it makes my life a lot easier, right? We're going to do that swappy game that we played where our charges are dropped down to be our subscripts for our formulas. NaNO3, and then it's PbI2 for my lead 2 iodide. Again, all about our charges. We played this game at the very beginning, coming back to haunt us here, right? We can't forget how to put together our compound formulas. All right, so we're going to swap our cations. Once we swap our cations, we can create our product formulas. All right, and honestly, that's the hard part. If we get that part, we're sort of good to go from here, but we're not quite done. What is this chemical equation missing? States of matter on those products. What else am I going to need to do to finish this off? To balance it, all right? So what we're going to do first are the states of matter. And what we need to do is we need to look up each of our products on that solubility table. Last class, we worked on using that table to classify solids as being either soluble or insoluble. We're going to play the exact same game with these two products that we just created. All right, I'm going to go to my solubility table here. And ignore all this. And for these two compounds, I'm going to classify them as being either soluble or insoluble? So everybody take a second. Sodium nitrate and lead 2 iodide, are they soluble or insoluble according to our table? Sodium nitrate, what do we got? Soluble. We could look up either our sodium ion or our nitrate ion and see that there are no insoluble exceptions. And what about that lead 2 iodide? All right, so we look up our anion, the iodide, and this tells me that most iodides are soluble, but there's an exception for iodides that are paired with silver, mercury, or lead, and this is, of course, lead, so this is insoluble. All right, so this will help us determine our states of matter here. Remember, soluble meaning that it will dissolve in water, so that means we can create an aqueous solution with our sodium nitrate. But insoluble means that it is not soluble in water, it will not dissolve in water, and so this tells me what my solid precipitate is, right? That insoluble compound is going to be what precipitates out in your solution, right? That's what gets that S state of matter. So using my solubility table here, I know that my sodium nitrate is aqueous and my lead 2 iodide is that solid product that makes this a precipitation reaction. Cool? So now we got our states of matter. The last step, balance, yes, okay, everybody take a second and balance this chemical equation. All right, so I need a 2 out front of my sodium iodide on the reactant side, and then a 2 out front of the sodium nitrate on the product side to balance this out. All right, so just to kind of finish up our rules here, we said states of matter, look up each product on our solubility table. Soluble means we're going to denote it with what 2 letters? AQ. And insoluble means that is our solid product. All right, and then the very last step so that we can use it is to balance. Okay, so with these double displacement reactions, we have the ability to predict the products of these double displacement reactions following this pattern that we laid out at the beginning. All right, and what we're going to do is when we're putting these formulas together for our products, it's all about the charges. So step 1 is to break up those reactants into their cations and anions with those charges written down so you can see. Then you'll swap your cations and create your product formulas. From there, you've done the hard part. Now you just need your states of matter. You'll look those up on your solubility table and then finally balance that chemical equation. Okay? All right, I'm going to let you all do one more on your own here. Okay, again, I'm going to give you your reactants. We're going to do silver chlorate and potassium bromide. chlorate, yeah. Right, yeah, so ClO3, what the heck is that? A chlorate ion. That's not one of the ones I told you had to have memorized. Where are you supposed to figure out what that is? Solubility table. Alright, so my silver ion has a +1 charge, my chlorate ion has a -1 charge, potassium has a +1 charge, and bromide has a -1 charge, and I'm going to swap my cations, swap my silver and my potassium. So now my potassium is with that chlorate, and my silver is with that bromide. So I'm going to take my two products here, and I'm going to go turn to that constants page, that solubility table. I'm going to look up these two here, stack them so I can move them up here. Okay. Potassium chlorate, soluble or insoluble? Soluble. Turns out that all chlorates are soluble, so are all potassiums. So what would be my states of matter on that one? AQ. And what about the silver bromide? Silver bromide. Bromides, most of them are soluble unless they're paired with silver, mercury, or lead. So this is one of my insoluble exceptions. All right. So this is AQ. And this is my solid here. These are all actually 1 to 1 to 1, so we're already all sort of balanced here. Okay, cool. So now I just want to sort of make sure visually, like from a mental image, we can kind of see what's going on. All right, this is sort of rooted in what we learned last class with regard to what happens when you take an ionic compound and you make an aqueous solution with it. All right, so I'm going to picture my silver ions in blue and these chlorate ions in green. So this is my silver chlorate compound right here. And my potassium ions we're going to show in red, and my bromide ions we're going to show in orange here. All right, I'll write in a little plus and minus so we remember who's who here. Cool, so I take this silver chlorate and I add it to my solution here. What's going to happen to that ionic bond when I take this silver chlorate and dissolve it into water? It's going to dissociate, absolutely. So I'm going to have my silver ions floating around. I'm going to have my chlorate ions floating around. but they're no longer going to be bound to one another. They're floating around all independently. So then if I mix in my solution, my aqueous solution, I'll have these potassium ions floating around and these bromide ions floating around. Okay? So I just have this mixture of these two ionic compounds here. But now let's look at what's going to happen on our product side. Okay? What our products are telling us is that silver bromide is a solid. So when those silver ions find those bromide ions, they're going to bind together. So I no longer have this aqueous solution. Now I have these ions that are stuck together. And they're just going to keep on going and going and going. Right? And so what I'm going to do is I'm going to form solid silver bromide. That solid will start to collect and settle in the bottom of our beaker here. Right? When a silver ion finds a bromide ion, they're going to reform that ionic bond. This is not a soluble ionic compound. And so we're going to get this repeating array of positive and negative charges. What about my potassium ions and my chlorate ions? Are they going to be stuck together? No, because this is still an aqueous compound here, which means that I still have my potassium ions and my chlorate ions just kind of floating around independently of one another. All right, so in this reaction, we had all these ions, and they used to be floating around all happy and individual, but as soon as a silver and a bromide find one another, they're going to stick together and form this solid that will start to collect at the bottom of our beaker, this precipitate. Okay, cool. Let's just do a little bit more practice here before we move on. Whoops. Sodium sulfate plus barium nitrate Sorry, I need states of matter. AQ, always aqueous solutions that you're mixing together. right, so I broke the sodium and the sulfate up looking at their charges and the barium and the nitrate. And now I'm going to swap my barium and my sodium. So now I have barium with sulfate and sodium with nitrate. Barium's got a +2 charge, sulfate has a -2 charge, so that's just BaSO4, and sodium nitrate, NaNO3. Okay, so now going to our solubility table here. I don't know if I'm all that creative because I think we've looked up sodium nitrate before. And which is that, soluble or insoluble? Soluble, because not only are all nitrates soluble, but so are all sodium compounds. But what about barium sulfate? All right, so we're going to look up that anion, that sulfate ion, right here. This tells me that most sulfates are soluble, but one of the exceptions is barium sulfate. All right, so sodium sulfate is soluble, but barium sulfate is insoluble. So this will be my solid, and this will be my AQ. And then I'm done. What's the last thing? We got a balance. All right, this one's not too bad. I just need a 2 over here on my product side to balance out my sodiums and my nitrates. Okay, so again, we can predict, given these two solutions that we mix together, we can predict our products of these precipitation reactions. We do our double displacement swap to get our compound formulas, and then we look them up on our solubility table. All right. For this one, I'm going to go a little bit quicker through this. Again, I started that same process, broke up these compounds into these two constituent ions with their charges, and then swapped. So now I have my potassium with my acetate and my cesium with my chlorate. So again, we're going to go to our solubility table here. All right, potassium acetate. What is that, soluble or insoluble? Soluble. So if we look up our acetate ion or potassium, they both tell us the same thing, which there are no insoluble exceptions. And what about our cesium chlorate, soluble or insoluble? That one's also soluble. Again, all chlorates and all cesium compounds are soluble. All right, so if they're both soluble, they should both get which designation here? AQ. All right, so what gives here? So let's go back to our little mental image here of our mixture of our ionic compounds. All right, we took these ionic compounds and we mixed them together, so now we have all these ions individually floating around. But nothing happens, right? We don't have any solid that's formed. There's no new chemical bonds that are formed. All we have are a bunch of potassium, cesium, acetate, and chlorate ions floating around independently of one another. So there's been no chemical reaction that has occurred here at all. No new bonds have been formed. I just got a bunch of ions floating around, all right? So in this case, we don't even bother trying to say that we're trying to get our balanced chemical equation. Once we look them up and they're both aqueous, we're going to stop right there and say no reaction. Okay? If you have no solid product that's formed, then there's no chemical reaction that's occurred. All you've done is mix two solutions together. And our chemical equations are specifically there to show chemical reactions, right? So in this case here, we would simply stop and say, nope, there is no reaction that occurs. All right, and again, to be clear, no reaction means that both products are aqueous. Okay, that's also why we save the balancing for the end. We'll look up the states first, and that way if we find out that there's no reaction, we didn't waste our time balancing that chemical equation. Cool, all right. So precipitation reactions are a type of double displacement reaction. We learned how to predict the products by using the fact that it's a double displacement reaction as well as looking them up on our solubility table. There's another subcategory of these double displacement reactions that we're going to talk about, and those are what are called acid-base reactions. All right, also double displacement reactions. All right, but another subcategory here. Okay. You will discuss acids and bases in like just about every class in your chemistry career. And so what we're going to do is like introduce them very simply for the start, and then you'll build off that concept and sort of complicate things in the future. All right? So for right now, our acid okay. We're going to use this phrase, acid is an H+ donor. All right, let's look at an example here. HCl, hydrochloric acid. Is this molecule covalent or ionic? Right? Hydrogen's a nonmetal, chlorine's a nonmetal, all right? So these acids are covalent compounds, but there's something really weird about these acids, which is they are covalent compounds, but they still dissociate in aqueous solution. Okay? They behave like ionic compounds in water. They actually still split up. So this would split up into a hydrogen ion and a chloride ion. All right, we spent a lot of time last class talking about what these solutions look like. And we said ionic compounds dissociate in solution. But we made a point to sort of bend over backwards to say covalent compounds do not. Covalent bonds don't break when you make a solution with them. All right, acids are the exception to that rule. An acid is a covalent compound, but a covalent compound that will dissociate in aqueous solution. Okay, we call it an H+ donor because, again, it's going to shed this H+ ion here, this hydrogen ion. Okay, so then a base is a soluble hydroxide compound. Okay, so a base is something like, for example, sodium hydroxide. Any hydroxide compound that contains a hydroxide, but is soluble, is going to be considered a base. Right? And like all ionic compounds, this can dissociate in solution into sodium ions and hydroxide ions. Okay, so let's do a sample reaction here. We'll use these two that we just laid out. HCl plus NaOH. Using this double displacement scheme. Again, just like our precipitation reactions. These are double displacement reactions. Take a second and try to predict the products of this reaction here. so now I'm going to swap my cations here. I'm going to pair my sodium with the chloride and my hydrogen ion with the hydroxide ion. All right, so hopefully we've beaten NaCl to death here. We know that our formula is NaCl. Okay, we can look it up on our solubility table to find that this is indeed a soluble compound. All right, and then my other product is HOH, which is a really weird way of writing the formula for what molecule? H2O, water here, right? So, an acid-base reaction is a reaction where you take an acid and a base and they combine together to make some salt, some ionic compound, and water. I've been using these AQ designations, but for water, remember to be an aqueous solution. That means it's a water-based solution. You can't have a water solution of water, right? So if you're making water molecules in an aqueous solution, you are just making liquid water. Okay, and again, we'll sort of complicate things and expand our understanding of acids and bases as we go here. But for right now, we can just say that an acid-base reaction, acid plus base, produces salt plus water. And in this particular case, it was actually sodium chloride. It was table salt. But remember, in chemistry, by salt, I just mean some ionic compound. And even say specifically it'll be an aqueous. Well, I guess I can't say that. We got to look it up on our table. Cool. All right, let's just practice this one more time. It's all about writing these chemical equations given just the reactants here. So now I want you to practice. We're going to use nitric acid and barium hydroxide . need to put my 2 plus barium with my 1 minus nitrate, so I'll need 2 of them. That's AQ. And then my hydrogen ion and my hydroxide ion will form liquid water. Am I done? Close, but I gotta balance this chemical equation. Don't forget that very last step here to balance your chemical equation. Since I had 2 hydroxides in this reaction, I'm gonna need 2 of my hydrogen ions, and that will make 2 water molecules. Cool? All right. So, what's up?
What would that look like? Like, you know how you put each element down and then you put the...
Yeah, so
how
kind of
would
the
that look
easiest
on
way to do it would be to keep track of H's, OH's, bariums, and nitrates, and consider water to be HOH. Because yes, there's a lot of hydrogens and oxygens floating around. What you'll also sort of always see, and maybe we can just lay this out to be clear, is that when you're done balancing, the number of hydrogen ions has to equal the number of hydroxide ions, because they react 1-to-1 to form water. And this will then also equal the number of water molecules that you get on your product side. Because again, each water molecule is formed by 1 hydroxide finding 1 hydrogen ion. Right? So you can also kind of maybe use this to sort of double check things as well. Make sure you have the same number of hydrogen ions from your acid as you have hydroxides from your base, and this will equal the total number of waters that you have on your product side. Cool. All right, so one more skill that we're going to learn how to do with these double displacement reactions. Really, we can do this for any reaction, but we're going to use our double displacement reactions to write what are called net ionic equations. Okay. All right, and this is similar to something we did before. We wrote these balanced dissociation equations. When we were looking at our ionic compounds, we said, for example, NaClAQ is the same thing as having an aqueous sodium ion and an aqueous chloride ion floating around independently of one another, right? That's what it meant to be NaClAQ. We have these 2 separate ions. Okay, we want them to be balanced though. NaCl was just 1-to-1, so now let's say we take something like rubidium phosphate, AQ. Everybody take a second and write my balanced dissociation equation here. So this is going to break up into rubidium ions, which have a +1 charge, and phosphate ions, which have a -3 charge, okay? But I gotta keep things balanced here, all right? Previously, when we were breaking stuff up, we were kind of being lazy, because the only thing we cared about were our charges so that we could match these things back up, right? Here, we need to make sure to keep track of how many of these rubidium ions we have. According to my formula here, I have 3. So that means when this thing dissociates, it will dissociate into 3 rubidium ions and 1 phosphate ion. All right, so notice how the number of rubidiums in my formula is going to become a coefficient when I do my dissociation equation. All right, I got 3 of them, so when it breaks up, I need to show that there are going to be 3 rubidium ions floating around. All right, this is going to be a very similar skill to what we're going to need for writing net ionic equations. All right, we're going to take an example chemical equation. We'll do one that we sort of already balanced. We already went through. We'll use our silver chlorate. This guy here is a good example. All right, I'm going to leave some room for some rules for writing net ionic equations here and do my example a little bit lower. All right, this is what we call our balanced chemical equation. We just did a lot of work for writing balanced chemical equations for this specific type of reaction, given just those 2 reactants. Okay, so now we're going to take this balanced chemical equation and we're going to first turn it into what's called an ionic equation. And then we're going to take that ionic equation and create what we're going to call our net ionic equation. All right, so for writing net ionic equations, again, step 1 is actually to first write your ionic equation. All right, so how do we do that? We're going to break up all aqueous compounds. All right, we want to make a note that we have to do so in a balanced way into cations and anions. All right. Now, before we go on, let's just sort of make special note here, only the aqueous compounds. Right? Those are the only ones that you're going to break up. If it's not aqueous, otherwise, you're just going to copy and paste the formula from your chemical equation. Alright, so we gotta look. Again, we say we're gonna break up all of our aqueous compounds. Again, only the aqueous compounds are gonna get broken up. If it doesn't have that AQ, you're just gonna copy and paste it down into your ionic equation. The other thing we wanna make a note of, because this is also something that people do a lot incorrectly, we're gonna break it up into cation and anion, which remember means we do not break up our polyatomic ions. That phosphate ion is your anion. You don't break it up into individual phosphoruses and oxygens. It's a package deal. All right, so I'm going to do the first one together, and then I want you all to do the next one on your own here. I'll focus on our first aqueous compound, the silver chlorate. So I'm going to break this up into the silver ions with their charge, and the chlorate ion with its charge. Right? So in my balanced chemical equation, AgClO3AQ becomes the silver ion plus the chlorate ion. All right, so now y'all are going to do the same thing for the potassium bromide here. We're going to just line them all up in our new chemical equation, our new ionic equation here. Alright, so now we got a potassium ion and a bromide ion. So I took my KBr from my balanced chemical equation and I broke it up into potassium ions and bromide ions. Alright, now we're going to draw a reaction arrow and we're going to jump to the other side of our chemical equation. This potassium chlorate, am I going to break it up? And how do I know I'm going to break it up? Because it's AQ. All right, so now we're on our product side. I'm going to break up that potassium chlorate. And I'm going to break up my silver bromide. No, because that is not aqueous. It's got that solid. So all you're going to do is copy and paste that formula. AgBr S as is. What's up?
What about water?
Liquid, right? So don't break it up. No, only if it has that AQ designation. Cool. All right, so now I have this all broken up here. I have what's called my ionic equation. Now we're going to take that and form what's called our net ionic equation. Okay, and to get that, we're simply going to cancel the exact matches matches ES?
Yes.
Okay. That appear on both sides of that ionic equation. Right, so we broke up all of our aqueous compounds to get our ionic equation. To get our net ionic equation, we need to cancel the things, the exact matches that are on both sides. So let me just show you what I mean real quick. I'm going to copy and paste them and get rid of all this coloring here so we can see a little bit easier what's going on. Okay. I need to get rid of exact matches that appear on both sides. I got two things that I can cancel here. Who sees one of them? My potassium ions, K plus 1 AQ, K plus 1 AQ, exact match, get rid of it. What else can I get rid of here? The chlorate, ClO3 minus 1 AQ, ClO3 minus 1 AQ, get rid of it. What about my silver? Can I cancel this out? I see silver over here and silver over here. No, they're not exact matches. One of them is an aqueous silver ion, the other one is silver in silver bromide. Okay, so these are the only two things that I can cancel. Once you're done canceling, you're going to rewrite, and that is your net ionic equation. Silver plus bromide gives you silver bromide, solid silver bromide. Okay, boom, final answer, my net ionic equation. Okay, and we like our net ionic equation here because it shows us what's really happening in this chemical reaction. Our chemical reaction here is all about those silver ions, finding those bromide ions and forming solid silver bromide. These things that we crossed out, the potassium and the chlorate. What are they doing in this chemical reaction? Absolutely nothing. They are just sitting there floating around. They are watching the reaction take place, but they themselves are not participating. This is what we call spectator ions. So my potassium and my chlorate, the things that I'm able to cancel out from my ionic equation, we call spectator ions. Okay, and again, as the name implies, they're called spectator ions because they're just sitting there watching the show. They're not actually participating in the chemical reaction at all. All right, so you're going to do one more from scratch for me here. I'm going to give you our reactants, strontium chloride and lithium phosphate. You need to first write me a balanced chemical equation using how we discussed predicting these products. And then from there you can write me an ionic equation and then finally a net ionic equation. Did anybody not get one of the periodic tables with that solubility chart on the back? Pass that over to me, thank you. Can you pass that down for me? everybody take a second. Let's make sure we got the same balanced chemical equation here. Importantly, when I do my products, that would be lithium with my chlorides, so LiCl. And my strontium phosphate, remember how I get my formula? I need to bring down that 3 and bring down that 2. So then when we balance our chemical equation, I'm going to need a 3 out front of the strontium chloride and a 2 out front of the lithium phosphate on my reactant side. And that would make 6 lithium chlorides on my product side and one of those solid products. Okay? Let's do this first ionic step together, because this is going to be a little bit tricky because we don't just have 1 to 1 to 1 like we did in our previous example. I need to make this ionic equation balanced, right? So I'm going to use with my balanced chemical equation up above. How many strontium ions do I have according to that balanced chemical equation? 3. So when I write my ionic equation, I'm going to write 3 strontium ions with their +2 charge. And what about chloride ions? How many chloride ions do I have? Yeah, if I have 3 strontium chlorides and each one contains 2, that means I will have a total of 6 chloride ions in my ionic equation, my balanced ionic equation. All right, okay, cool. I think y'all can finish it off, but just keep a note, we're going to have to pay attention to our coefficients from our balanced chemical equation, as well as our subscripts from our formulas. Okay, so I got my ionic equation by separating all my aqueous compounds. Notice that solid over there is going to stay together when I do my ionic equation. I only break up the aqueous. So then to do my net ionic equation, now I'm going to cancel everything that's on both sides, my exact matches from both sides. What's one thing I get to cancel? My chlorides will cancel out. I got 6 Cl minus 1 AQ, 6 Cl minus 1 AQ. What else? The lithiums. 6 Li plus 1 AQ. So my final balanced chemical equation here are these 3 strontium ions, rather my net ionic equation here are these 3 strontium ions plus these 2 phosphate ions to give me my solid strontium phosphate. That's my net ionic equation. Cool. Any questions? All right, so just to review what we did today, We talked about double displacement reactions, and we introduced two specific categories of double displacement reactions: precipitation reactions, and again, we can predict the products. We're going to break up those compounds to get our product formulas. We're going to look up their states of matter on the solubility table and then balance those chemical equations, right? So this is now another reaction that we can predict the products for. And then we played this similar game with an acid-base reaction. We introduced what acids and bases were. Acids are hydrogen donors. They're ionic, or they're covalent compounds, but they behave a lot like ionic compounds in that they dissociate in aqueous solution. And when we react those with the base, that hydrogen ion and those hydroxide ions come together to form water. Okay? So we can write our balanced chemical equation for those acid-base reactions as well. And then we learned how to take a chemical equation and to find its net ionic equation, first by writing an ionic equation, a balanced equation where we break up all those aqueous compounds into their cations and anions, and then we cross out what's on both sides, and that leaves us with what is like the meat of the reaction here, your net ionic equation. Right? So in that last example, it's those strontium ions finding those phosphate ions to become solid strontium phosphate. The lithium and the chloride we would call what? Just spectator ions. They're not actually involved in the reaction at all, right? So when we cross them out, we call those spectator ions. Cool. Great.